Calculus, video 9 on limits. So two ways we'll look at limits. One, at least in this first part, we'll evaluate them numerically by numbers, plugging in different numbers. And second, we'll evaluate limits analytically. Or another way to think about analytically is using algebra. Eventually, we'll go more towards the analytical side and not use as much just plugging in numbers for the numerical part. But at least to start off, it kind of gives us an idea of what's happening with limits. So we'll just start with an example. In this case, function f of x is equal to x squared minus 3x minus 10 divided by x plus 2. So you have some rational function here. And what we want to know is, what is the limit as x approaches negative 2 of x squared minus 3x minus 10 divided by x plus 2? The first thing I recommend is something called direct substitution. So this is what we often try first, meaning is our x value gets close to negative 2, it's negative 1.999, negative 2.001, or as the x is getting really close to negative 2, maybe we just plug in negative 2. We let x get close to negative 2 in our function and see what happens. So for example, if I let x go to negative 2, I would get direct substitution, basically plugging in negative 2 for the x's. Negative 2 squared minus 3 times negative 2 minus 10 divided by negative 2 plus 2. And if I multiply that out, negative 2 squared is 4, negative 3 and negative 2 is positive 6 minus 10, and in the denominator negative 2 and positive 2 is 0. 4 plus 6 minus 10 is also 0. We get what's called 0 over 0, or indeterminate form. 0 over 0, this indeterminate form, means we're not exactly sure how this is going to turn out. Our actual answer could be 1, or 7, or 3 halves, or infinity. Right? We're just not sure. We can't determine it. So, indeterminate form. And what's really happening here, oftentimes when we have the 0 over 0, is there's a hole in the graph. And in that case, that's good for us, because when there's a hole in the graph, the limit will exist. All right, picture some random curve here that's going along and a hole in the graph at the particular a value that we're limiting towards. The limit, as we approach that value a from the left, the y value, the function value, gets close to a specific number. You put more of a graph on here. The y value is approaching, whatever this, say, L value is. That it's approaching a particular y value, and also from the right, the function is approaching that same value L. When I use the words from the left, what you're picturing is the left side of A. You're picturing kind of as the curve is approaching the value, the x value, the value of the function at x equals A. Even if that value doesn't exactly exist, the limit from the left, you're picturing from the left-hand side of A, what happens on the curve as the x values get close to A. And when I say from the right, so that would be from the left. From the left. And when I say from the right, you're picturing the values on the curve, the values of the function as the x values get close to A. And in both cases, from the left and the right, we can see that the function values are approaching L. The good thing about having a hole in the graph when you're talking about limits is limits don't care what happens at A, right? X is only approaching negative 2. It doesn't care what happens at negative 2. So the fact that there's a hole in the graph, no big deal for limits. We only care what happens as the x value approaches the A value anyway. Okay, so we've determined that our limit here is indeterminate. There's more than likely a hole in the graph. The limit now will probably exist. Meaning we'll be able to get an answer. So what is that limit? Well, often we can now do some algebra. So we'll do this analytically first. And one of these things we'll see is it's a polynomial in the numerator, a polynomial in the denominator. Maybe if we factor, one of those terms will cancel out, which is what will happen here. So we have, this is the limit as x approaches negative 2. I'm going to take my numerator x squared minus 3x minus 10. I'm going to factor that. That factors into x minus 5x plus 2. And my denominator is just x plus 2. Again, if I would have plugged negative 2 in for all the x's, I would still get 0 over 0. But now, because I have the x plus 2 and x plus 2, they can cancel out. And we're just left with the limit as x approaches negative 2 of x minus 5. Now that I've canceled out the x plus 2, which is where there was a hole in the graph at negative 2 there, that term cancels out, we can now do direct substitution on the x here, plugging negative 2 in for x. So basically what we're saying is x is now going to negative 2. It's close to negative 2 as you want it to be. So negative 2 minus 5, negative 7, and we have evaluated the limit analytically. Maybe to give you kind of a picture of what's happening, believe it or not, this rational function x squared minus 3x minus 10 over x plus 2 is just a line. It may look more complicated than that, but because the x plus 2 terms cancel out, this x squared minus 3x minus 10 over x plus 2 can be simplified into the function x minus 5, which is what we did towards the end. So the graph of this function is no more than the graph of x minus 5, the line. Except the only difference is at negative 2, there is a hole in the graph. There's a hole in the graph, meaning that the function value at negative 2 does not exist. F of negative 2 does not exist. There is no y value for negative 2 because there's a hole in the graph. If we were to plug in negative 2, we get that 0 over 0. But the limit doesn't care about that. The limit just wants to know what happens from the left and the right as the x value approaches negative 2, both from the left, so coming in this way, and from the right, so coming in this way. We see that the function value approaches the y value of negative 7. Therefore, the limit as x approaches negative 2 of that particular function is negative 7. That would be solving the limit analytically, like we did above. If we wanted to solve it numerically, right, so if we want to do it numerically, this whole process up here was solving the limit analytically or algebraically. That was analytically. Numerically, we would simply plug numbers in next to negative 2, numbers that are really close to negative 2 to see what kind of value we'd get. So the function was, the original function, the limit as x approaches negative 2 of x squared minus 3x minus 10 over x plus 2. We would, technically you'd want to have several numbers you're plugging in. You want to plug in a number, several numbers to the right of negative 2, several numbers to the left of negative 2, so you can see kind of what is approaching. But oftentimes we get a little bit lazy and we just kind of pick a number on either side and see what happens. So for example, to the right of negative 2, let's try an x value of negative 1.99. It's pretty close to negative 2. So this is like from the right. And then from the left, something a little bit less than negative 2. Let's take a look at maybe x equals negative 2.01. And we plug those numbers into the function. We're approaching negative 2 from the right or left. We have negative 1.99 squared minus 3 times negative 1.99 minus 10. Let me grab my calculator. I don't know what that is. Sorry, calculator error for a minute. I think that my biggest problem is I forgot to divide by, I forgot the rest of my problem there, negative 1.99 plus 2. Missed the bottom part of that. Let's try this again. So in the numerator, when I multiplied that out, I got negative 0.0699, and then negative 1.99 plus 2 is 0.01, and when I divide that out, I get negative 6.99. And so we can see from the right-hand side, the value is, if you just move it just to the right of negative 2, is negative 6.99. And if you go just to the left of negative 2, same idea here, negative 2.01 squared minus 3 times negative 2.01 minus 10 over negative 2.01 plus 2. I'm getting 0.0701 divided by negative 0.01 this time, so negative 7.01. Again, from the left-hand side, it's approaching a y value of negative 7. That would be numerically. Numerically is good to kind of give an idea of what might be happening, but it's not like concrete proof that this goes into negative 7. I mean, it really looks like it does, but we solve it analytically to say, yes, it really does approach negative 7. The function here does as x approaches negative 2. Okay, let me keep the same problem, but let's approach a value that's not negative 2, right? At negative 2 is where we had the hole in the graph, and the limit still existed. What if we were to approach a different number? Let's say we approached an x value of 1, right? So we're approaching this point here. Notice that that point actually exists. The function exists there, right? You could plug 1 into the function. It has a y value. And also the limit exists. As we approach that from both the left and the right-hand side, right, it is going from both sides to a particular y value, whatever this y value is there. But because the function exists there, we can do direct substitution from the very beginning. So for example, if I have the limit as x approaches 1 of my function x squared minus 3x minus 10 over x plus 2, I'm going to first try direct substitution. I'm just going to plug the 1 in. What happens as x gets close to 1? Well, I get 1 squared minus 3 times 1 minus 10 over 1 plus 2. Notice that's not 0 over 0 this time. It is 1 minus 3 minus 10 over 3. What is that? That's negative 12 over 3. That's negative 4. The function actually approaches negative 4 as x approaches 1, and we can do that by direct substitution. So again, try that first, because if that works, then that's the easiest route. It's when you try direct substitution and you get something like we had the 0 over 0 up here, that indeterminate form, that's when you need to do some algebra or some analytical work to find the limit. Okay, let's try one more. How about the limit as x approaches 2 of 2 over x plus 2 minus x over 4 over x minus 2. Okay, looks a little complex, but I think we can handle it. Once again, I'm going to try direct substitution first. I'm going to let x go to 2, as close to 2 as I want it to be, so we're just going to let it be 2 at this point. That's 2 over 2 plus 2 minus 2 over 4 over 2 minus 2. That is 2 over 4. That's 1/2 minus 1/2 over 0. That's 0 over 0. That is indeterminate form. hole in the graph, that means our limit's going to exist. We just have to do some algebra to figure out what it is. All right, so last time we had a polynomial over a polynomial, so we factored the polynomials and then canceled out. When you see fractions like this, usually the best route to solving this is to find the common denominator of all the fractions. In this case, I have two fractions, so these are my two denominators, x plus 2 and 4. The common denominator would be 4 times x plus 2, and I'm just going to multiply top and bottom by that common denominator, 4 times x plus 2. That's going to look something like this. This is equal to the limit as x approaches 2 of 2 over x plus 2 minus x over 4 over x minus 2. And I'm going to multiply this by 1 in a sense of 4 times x plus 2 over 4 times x plus 2 is just 1. But this is the total, the common denominator of the whole problem. And when I do that, you'll see the denominators disappear for each individual fraction. Because 2 over x plus 2 times 4 times x plus 2, the x plus 2s would cancel. And we just get the limit here as x approaches 2. The x plus 2's cancel. 2 times 4 gives me 8. No fraction there. Minus x over 4 times 4 times x plus 2. The 4's cancel in this case, and I get x times x plus 2. And in my denominator, you actually don't want to multiply these out. You want to leave this as 4 times x minus 2 times x plus 2. Just all in this factored form here. The goal here, the hope here, is I'm eventually able to cancel out the x minus 2's. Okay, let's see what we have now. This is the limit as x approaches 2 of 8 minus x squared minus 2x over 4 x minus 2x plus 2. That's the limit as x approaches 2 of negative x squared. I'm going to factor out a negative 1 here because I don't like my x squared term to be negative. So x squared, that makes it a positive 2x since it was a negative 2x, and a minus 8 since it was positive 8 over 4 times x minus 2 times x plus 2. That's the limit as x approaches 2 of negative 1. Now I'm in polynomial, so x squared plus 2x minus 8. Let's hope that factors. I believe it does into x plus 4 and x minus 2. And this is why I don't want to multiply my denominator together, is because now I can cancel out the x minus 2's, leaving me with the limit as x approaches 2. Negative 1 times x plus 4 over 4 times x plus 2. And because we've canceled the x minus 2's, which is what was causing the 0 over 0, we can now plug 2 in for x. Negative 1, 2 plus 4, 4 times 2 plus 2. That is negative 6 over 2 plus 2, 4. 4 times 4, 16. Negative 3 eighths. Good. And you could solve this one numerically as well, but we're gonna show these analytically to have a more concrete answer of negative 3 eighths. We're still just estimating a little bit when we do it numerically. All right, maybe one more. One more, we'll call it good for this video. How about the limit as x approaches 6 of x minus 6 over the square root of x plus 10, and then outside the parentheses here, or sorry, outside the square root there, minus 4. And if you look at this, you can probably see this goes to 0 over 0. 6 minus 6, 0. 6 plus 10, 16. Squared is 4. 4 minus 4, 0. That is 0 over 0. So a little bit of algebra here. We'll take the limit as x approaches 6 of x minus 6 over the square root of x plus 10 minus 4. So you notice I'm doing 3 examples in this video, and these are the 3 most common algebraic techniques to solve these limits. Again, the first one is if you have polynomials, you factor them. Hopefully something cancels out. Second, if you have fractions, we're multiplying by the common denominator, top and bottom, by the common denominator of the entire problem. And thirdly, when we have square roots like this, what we often do is multiply by the conjugate of whichever term, top or bottom, numerator or denominator, that has the square root. In this case, my denominator has the square root of x plus 10 minus 4. So I'm going to multiply both top and bottom by its conjugate, square root of x plus 10 plus 4. All right, those are the three main ways we're going to solve these analytically. Once again, in my numerator this time, I don't want to distribute that out. I want to leave it. I only want to distribute, in this case, in my denominator, because multiplying by the conjugate gets rid of the square root. So we have the limit as x approaches 6. I'm going to leave the x minus 6 times the square root of x plus 10 plus 4 divided by, but my denominator I do want to distribute. So I have the square root of x plus 10 times the square root of x plus 10. That would just be x plus 10. The square root of x plus 10 times 4 is 4 root x plus 10. And then the negative 4 times both of those. Negative 4 times root x plus 10 is negative 4 root x plus 10. That was the whole point of the conjugate, is these two middle terms cancel. And negative 4 times 4 is negative 16. So again, the two middle terms cancel here. My denominator, x plus 10 minus 16. X plus 10 minus 16 is just x minus 6. Again, that's why we do not multiply out the numerator in this case, is we want to be able to cancel that x minus 6 with the denominator x minus 6. So I have in the numerator x minus 6 times the square root of x plus 10 and then plus 4. X minus 6 is cancel. I can now do direct substitution. Square root of 6 plus 10 plus 4. Square root of 16 plus 4. That's 4 plus 4. That's 8. And we have solved the limit.